As you know that we are discussing the unit solutions, dilute solutions and colligative properties. In this series, we have already discussed some colligative properties. In our last lecture, we discussed some examples of Raoult's law, measurement of relative lowering of vapor pressure and elevation in boiling point. In today's lecture, we will continue discussing the elevation in boiling point. Today, we will discuss thermodynamic calculation of molar elevation constant, measurement of elevation of boiling point, some examples related to elevation in boiling point. We will also discuss another colligative property known as depression in freezing point, and we will also derive an expression for depression in freezing point. Molar elevation constant is characteristic of a particular solvent and it is denoted as Kb equal to RTB square divided by 1000 into LV. Here Kb is molar elevation constant, Tb is boiling point of the solvent in Kelvin, R is gas constant and LV is latent heat of vaporization of the solvent. In case of water, this latent heat of vaporization is equal to 540 calories per gram. We can take R is equal to 2 calories per mole per Kelvin. The boiling point of pure water is 373 Kelvin. You must take R in the same units in which LV, that is latent heat of vaporization, is taken. If you are taking latent heat of vaporization in calories per gram, R must be taken in the units calories per mole per Kelvin. If you are taking latent heat of vaporization in joules per gram, R must be taken 8.314 joules per Kelvin per mole. So, for water, we are taking R is equal to 2 calories per mole per Kelvin, LV equal to 540 calories per gram, Tb equal to 373 Kelvin. Putting these values in the expression for thermodynamic calculation of elevation in boiling point, we will get Kb equal to 0.515 Kelvin kg per mole. You can see the values of molar elevation constants for some solvents in this table. For water, it is equal to 0.52 Kelvin kg per mole. For acetone, it is equal to 1.70 Kelvin kg per mole. Similarly, you can have a look for chloroform, carbon tetrachloride, benzene and ethyl alcohol. If molar elevation constant increase in boiling point, that is elevation in boiling point, weight of solvent and weight of solute are known, the molecular mass of non-volatile solute can be determined experimentally. The most convenient method for determination of delta Tb is Landsberger's method. The method was introduced by Landsberger and modified by Walker. The apparatus for Landsberger's method consists of the inner tube with a hole in its side and graduated in ml, a boiling flask which sends solvent vapor into the graduated tube through a rose head. This is perforated. An outer tube which receives hot solvent vapor from the side hole of the inner tube. A thermometer reading to 0.01 Kelvin dipping in solvent or solution in the inner tube. The pure solvent is put in the boiling tube and the vapors of the same solvent which is boiling in another flask is passed through the solvent. These vapors cause the solvent to boil, and when the temperature becomes constant, the boiling point is recorded. Now, some weighed amount of solute pellets is introduced into the boiling tube, and the boiling point of the solution is recorded in the same way. After that, thermometer and rose head are removed and the volume of the solution is recorded. By this volume, we can calculate the mass of the solution. By the difference of boiling point of solvent and boiling point of solution, elevation in boiling point can be calculated, and this can be put into the relation delta Tb is equal to Kb into molality of the solution. By using this relationship, we can calculate the molecular mass of the solute as Ma, which is equal to molecular mass of the solute is equal to 1000 into Kb into Wa divided by Wb into delta Tb. Here Wa is the mass of solute, Wb is the mass of solvent, and delta Tb is elevation in boiling point. A method better than Landsberger-Walker method was devised by Cottrell in 1910. You can have a look on this figure for the apparatus of this method. The apparatus of Cottrell's method consists of a graduated boiling tube containing solvent or solution, a reflux condenser which returns the vaporized solvent to the boiling tube, and a thermometer reading to 0.01 Kelvin enclosed in a glass hood, a small inverted funnel with a narrow stem. Beckmann's thermometer is a thermometer devised to measure the difference in the temperature and not the actual temperature. The unique feature of this thermometer is the small reservoir of mercury at the top. We can set the level of the mercury thread in the thermometer by gently tapping the thermometer. In this way, the level of the mercury thread can rest at the desired position. For measurement of delta Tb, that is change in boiling point of solution with Cottrell's method, the solvent is placed in the boiling tube with a porcelain piece, and this solvent is gently heated with a small flame. As the solvent boils, the porcelain piece pumps the boiling liquid into the narrow jet. Now, the vapors from this narrow stem and the boiling liquid is regularly sprayed around the thermometer. As the temperature becomes constant, the temperature is red. Similarly, the temperature is red for the solution also. For making the solution, some small amount which is weighed accurately is introduced into the boiling tube, and the temperature is recorded in the similar way as we recorded the boiling point of the pure solvent. Now, from the boiling point of that of solvent and of solution, the elevation in boiling point is calculated. As the boiling tube is graduated, the volume of the solution is recorded to calculate the weight of the solution by using the density of the solution. We can practice some examples related to elevation in boiling point. The first one is a solution of 2.5 grams of a non-volatile solute in 100 grams benzene boiled at 0.42 degrees Celsius higher than the boiling point of pure benzene. Calculate the molecular mass of the substance. Molar elevation constant of benzene is given equal to 2.67 Kelvin kg per mole. We can use the expression as delta Tb is equal to Kb into molality, from which we can get another expression Ma equal to 1000 into Kb into Wa divided by Wb into delta Tb. Ma is the molecular mass of the solute and Wa is the weight of solute. Wb is the weight of the solvent. Hence, by using all these values which are given in the problem, we can get the molecular mass of the solute equal to 158.9 grams per mole. Another example, the molar elevation constant for water is 0.56 Kelvin kg per mole. Calculate the boiling point of a solution made by dissolving 6 grams of urea in 200 grams of water. Molecular formula of urea is given as NH2CONH2. You can calculate the molecular mass of urea, which comes out to be equal to 60. Now, by using the same relationship as delta Tb is equal to Kb into molality. Molality is number of moles of solute divided by kg of solvent. From that, we get the relationship delta Tb is equal to 1000 Kb into Wa divided by Ma into Wb. Kb is given 0.56 Kelvin kg per mole. Wa, that is weight of solute, is given 6.0 grams. Wb, that is weight of solvent, is also given 200 grams, and molecular mass of solute, that is the molecular mass of urea, is equal to 60. Now, by putting all the values in the relationship, you can get the value of delta Tb equal to 0.28. This can be taken in degree Celsius or Kelvin both, because the size of the degree in Kelvin scale and Celsius scale is same. Thus, the boiling point of the solution will be equal to normal boiling point of water plus increase in boiling point. Normal boiling point of water is 100 degrees Celsius and increase in boiling point will be equal to 100 degrees Celsius plus 0.28 degrees Celsius, which will come out to be 100.28 degrees Celsius. You can practice some more examples related to elevation in boiling point. A solution of 3.8 grams of sulfur in 100 grams of carbon disulfide boils at 46.66 degrees Celsius. The boiling point of pure carbon disulfide is 46.30 degrees Celsius. What is the formula of sulfur molecule in this solution? Atomic mass of sulfur is given as 32 grams per mole and Kb for CS2 is also given as 2.40 Kelvin kg per mole. You can use the same relationship, that is delta Tb is equal to Kb into molality. By that relationship, you can get Ma is equal to 1000 Kb into Wa divided by Wb into delta Tb. Here Wa, that is weight of solute, is given as 3.8 grams and molar elevation constant is given as 2.4 Kelvin kg per mole. So, you can put these values in the relationship and calculate Ma, which is the molecular mass of the solute. You will get Ma equal to 253 grams per mole. Now, atomicity will be equal to molecular mass upon gram atomic mass. Molecular mass you get 253 grams per mole. Divide the molecular mass by atomic mass, which is equal to 32. So, you will get a value which is approximately equal to 8. Hence, the atomicity of sulfur will be equal to 8 and the sulfur molecule exists as S8. There is another example. Sucrose, that is cane sugar, having molecular mass 342 grams per mole, is highly soluble in water. Almost 2000 grams will dissolve in 1 liter of water. Estimate the boiling point of such a sugar solution. Now, moles of sucrose will be equal to 2000 grams divided by 342, which is the molecular mass of the sucrose. Moles of sucrose will come out to be 5.8 moles. Mass of water, we have assumed 1000 grams because we know the density of water, which is equal to 1 grams per ml. the molality of the solution will be equal to 5.8 divided by 1 kg of water, which is equal to 5.8 molal. Using the relationship for delta Tb, we will get the value of delta Tb equal to 3.16 Kelvin or 3.16 degrees Celsius. Hence, the boiling point of this solution will be equal to 100 plus 3.16 degrees Celsius, that is 103.16 degrees Celsius. Now, we are going to discuss another colligative property. Before going to the next colligative property, you must recall that the vapor pressure of a solution is lower than the vapor pressure of pure solvent. The lower vapor pressure of the solution is because of the competition between the solute molecules and solvent molecules to escape from the surface of liquid. In solutions with non-volatile solutes, it is the solvent only which freezes. Let us define the freezing point before going to the colligative property depression in freezing point. Freezing point is the temperature at which the solid solvent comes out of the solution, or we can say that the freezing point is the temperature at which the vapor pressure of solid phase is equal to the vapor pressure of the liquid phase, which is in dynamic equilibrium with the solid phase. At the freezing point of the solution, there is an equilibrium established between the solid solvent and the liquid solvent. There is also an equilibrium between the number of particles of solvent leaving the solution and number of particles of solvent returning to the solution. As the vapor pressure of the solution decreases on adding a non-volatile solute, hence the temperature at which it comes in dynamic equilibrium also decreases. Therefore, the freezing point of the solution decreases, which is known as depression in freezing point. You can have a look on this vapor pressure versus temperature phase diagram. Vapor pressure of solution decreases, because of which the freezing point of the solution also decreases. Now, we are going to derive an expression for the calculation of depression in freezing point. We will take delta Tf equal to depression in freezing point, which will be equal to the freezing point of the solvent minus freezing point of the solution. This can be better understood by plotting a graph between vapor pressure and temperature for pure solvent and two solutions, solution 1 and solution 2. Here solution 2 is more concentrated than solution 1. BA is the graph for pure solvent. From F, it is for solution 1, and from C, it is for solution 2. CFB is a curve for solid solvent. For the solvent, solution 1 and solution 2, vapor pressure curves meet CFB curve at point B, F and C respectively. Thus, T0, T1 and T2 are the freezing points for the solvent, solution 1 and solution 2. The vapor pressures for pure solvent, solution 1 and solution 2 at their freezing points are thus P0, P1 and P2 respectively. For very dilute solutions, the curves FD and CE are almost straight line and BC is also nearly a straight line. Therefore, the triangle EBC and triangle DBF are similar. Hence, from the properties of similar triangles, we have EC upon DF equal to BE upon BD, which is again equal to T0 minus T2 upon T0 minus T1. equal to P naught minus P2 upon P naught minus P1. Now, T naught minus T2 is the depression of freezing point for second solution and T naught minus T1 is the depression in freezing point for first solution. Similarly, P naught minus P2 is the decrease in vapor pressure for second solution and P naught minus P1 is decrease in vapor pressure for first solution. Therefore, from this relationship we can have delta T2 upon delta T1 equal to delta P2 upon delta P1, or we can say that decrease in freezing point is directly proportional to decrease in vapor pressure. Hence, delta Tf is directly proportional to delta P. From Raoult's law for dilute solutions, we know that relative lowering in vapor pressure is equal to number of moles of solute upon number of moles of solvent. Therefore, we can have P naught B minus Ps equal to WaMb upon WbMa into P naught B. Here P naught B is the vapor pressure of pure solvent and Ps is the vapor pressure for the solution. For the pure solvent, P naught B and its molecular mass Mb will always remain constant. Therefore, P naught B minus Ps is directly proportional to Wa upon Ma into Wb, or delta P is directly proportional to delta Tf, which is directly proportional to Wa upon Ma into Wb. Putting a constant k, we will get an expression delta Tf is equal to k into Wa upon Ma into Wb. Here k is called depression constant. If we take 1 mole of solute, that is Wa upon Ma equal to 1 in 1 gram of solvent, which means Wb is equal to 1, delta Tf will be equal to k. Hence, k, freezing point constant, can be defined as the depression in freezing point when 1 mole of the solute is dissolved in 1 gram of the solvent. If we dissolve 1 gram of the solute in 100 grams of solvent, we will get delta Tf is equal to k upon 100. Here k dash is another constant which is equal to k upon 100. This k dash is known as molecular depression constant. K dash, that is molecular depression constant, is defined as the depression in freezing point which is caused when 1 mole of solute is dissolved in 100 grams of solvent. Similarly, if we dissolve 1 mole of solute in 1 kg, that is 1000 grams of solvent, we will get delta Tf is equal to k upon 1000. This k upon 1000 is again a constant which is replaced by Kf. This Kf is known as molar depression constant or cryoscopic constant. Molar depression constant or cryoscopic constant is defined as the depression in freezing point produced when 1 mole of solute is dissolved in 1000 grams or 1 kg of the solvent. Therefore, k is equal to 1000 Kf, and putting this value in equation 1, we will get delta Tf equal to 1000 into Kf into Wa upon Ma into Wb, or we can say that delta Tf equal to molality into Kf, as molality is equal to moles of solute upon kg of solvent, means molality is equal to Wa into 1000 upon Ma into Wb. The units of Kf, that is molar depression constant, will be equal to Kelvin kg per mole or degree Celsius kg per mole. Let us revise what we have discussed today. We have calculated molar elevation constant thermodynamically. The expression used was Kb equal to RTb square upon 1000 into Lv. We have also done two measurement techniques for the elevation in boiling point. These two techniques were Landsberger's method and Cottrell's method. Then we defined depression in freezing point and derived a relationship for the depression in freezing point. This relationship is delta Tf is equal to Kf into molality. We will continue discussing depression in freezing point in our next lecture also.